In the previous video on section 6.1, we looked at integrating with respect to x. Now we turn our attention to integrating instead with respect to y. This, of course, could be done with respect to x. If you wanted to do it with respect to x, you would have to make it into a compound region by splitting it where this blue shape and this orange shape cross. And then you would have to take the line y equal d and subtract the blue shape on the left and the line y equal d and subtract the equation of the line on the right. It can be done with respect to x, but this requires splitting it into two regions and two integration formulas. If instead we rewrite the equations as functions of y, the dependent variable, notice that we always have the line on the right and we always have the blue curve on the left. Then we can take this and represent it with one integral. Since we're going to integrate with respect to y, we'll draw the strips horizontally so that the narrow end becomes the differential dy. Notice that it is always the blue graph on the left and the orange graph on the right. This gives us one region to integrate over instead of two. However, it does require that we solve the equation for x in terms of y. Sometimes that's not easy to do. For example, let's go back to the one that I said might be easier with respect to y as opposed to x. And let's take a look at what it would take to solve those equations for x in terms of y. I believe that was this graph, example 5. Our two equations are y equal x squared minus 4x and y equal 2x minus 8. Notice that it is always the parabola on the left and the line on the right. If I come down here, and we're going to split this off, I have two equations, x squared minus 4x and y equal 2x minus 8. The line is relatively simple to rewrite in x in terms of y. It simply means that we're going to solve for x. To solve for x, I would move the 8 by adding it, and then I would divide by 2. This gives me that x is equal to 1/2 y plus 4. This would be relatively straightforward. The other function is not easy and not straightforward. Notice that it is a quadratic. However, we have a y in here. We need to solve for x, but because it's quadratic, we're going to have to use the quadratic formula, and y is going to become the constant term. We would have to move the y to the right and make it x squared minus 4x minus y equal to 0, with a equal to 1, b equal to -4, and c, the constant, equal to -y. Then, if we use the quadratic formula, we get the opposite of b plus or minus the square root of b squared minus 4 times a times c. And all of this is divided by 2 times a. This would give me 4 plus or minus the square root of 16 plus 4y, all divided by 2. Yeah, that's right. This would be the function on the left. Integrating this would not be pleasant. We could do it with u substitution. Note that we could let u be 16 plus 4y, and we could find du, which would be 4 dy. It can be done, but in this case, despite having to split it into two regions to integrate with respect to x, it is better than having to use the quadratic formula and integrating this more complicated integrand. Let's now return to our area between two curves. We're partitioning the interval on the y-axis, cutting up the region between y equals c and y equal d. Our interval over which we're integrating will be from c to d. And we'll take the equation of the function on the right and subtract the equation of the function on the left. And we'll use the differential dy. Let's take a look now at what the area of each strip would be. Again, this small amount of area on the side here is dy. And this distance here is actually the difference in the values of the functions on the left and the right. That right there is going to be right minus left. Oops, got the wrong letter. So the area of one strip becomes the right minus the left. Well, since it's a function of y, it's giving you the x value on the right minus x value on the left, which would give you this length times the differential dy. And then, of course, we add all the areas together between y equals c and y equal d. Let's take a look at the formal function. In this case, to find the area between two curves with respect to the dependent variable y, we write it so that we have one curve on the right, u of y, and one curve on the left, v of y. And we integrate from c to d. We subtract the left curve from the right curve. It is the same as finding the net area between the curve and the y-axis and subtracting the area between the curve of v and the y-axis, the net area. If we want to rename u and v, we can let the one on the right again be the larger one, since larger numbers are to the right, and we can let g be the smaller one, the one to the left. And then we end up with a very, very similar definite integral, but with respect to y instead, and integrating from c on the bottom to d on the top. If the graph does not give you the values of c and d in the problem, you'll have to take the values of c and d from where they intersect. In that sense, then you set the two equations equal to each other, but this time you solve for the y value where they intersect. Again, the value is going to be strictly positive because we're doing the right net area minus the left net area. The right net area must be greater than the left net area since it's further from the y-axis. Let's take a look at an example here. In example 7, we want to find the area between the curves given by y squared equal 4x and y equal 2x minus 4. This one is not yet solved for x, and this one is also not solved for x. When we look at this region, notice that if we were to do it vertically with respect to x, we would have to split it here where they intersect, because on the left side of that point, we have the parabola both above and below. Let's take a look at that now. If I went with respect to x, I would have the upper arm of the parabola on the left and the lower arm of the parabola on the bottom. And if I went with respect on the other side, with respect to x, I would have the upper arm of the parabola above and the line below. Now you may be going, well, how do you get the upper arm versus the lower arm? Remember that the equation was y squared equal 4x. This upper arm, which I'm going to highlight in blue, is given by the equation y equal the square root of 4x, the positive root. And the one below, which I'm going to highlight in yellow, is given instead by y equal negative the square root of 4x. So in order to do it with respect to x, I would instead have to split the integral here where they intersect with the line. And on the left, I would have the upper arm minus the lower arm of the same parabola opening to the right. And on the right side of where they intersect, I would have the upper arm of the parabola minus the line. Again, you would have to find the intersection point. We're going to need that anyway, so let's go ahead and find it. However, notice that in this case, if I'm looking for the intersection at the bottom, I use the lower function, negative root of 4x. In this case, I can now write y equal negative the root of 4x and y equal 2x minus 4 and set them equal to each other. This becomes a rather more complicated algebraic formula that we have to solve. In order to get at the x that's under the radical, yeah, you're right, you're going to have to square the sides. That can also introduce false solutions, so you've got to be careful. In this case, if we square both sides, then we can end up with 4x on the left, and on the right, when we square the sides, not the terms. That gives us 4x squared minus 16x plus 16. And we would have to get everything to one side, 0 on the other, and factor it. Every term is divisible by 4, so I'm going to take care of that common factor first. You're allowed to divide by a constant, but not anything involving the variable. This reduces the values, and now I can move the x to the opposite side to get, x squared minus 5x plus 4 equals 0, which factors as x minus 4, x minus 1. This gives me two possible solutions at 4 and at 1. When I look at my graph here, I can see that in fact I've found both of them. I've got the one down here at 1, and I've got the one up here at 4. In order to integrate with respect to x, I would then have to write the following integral. I would go from 0 to 1, and I would have the positive root on top minus the negative root on the bottom with respect to x, plus the integral from 1 to 4, and now the positive radical on top, which would be root of 4x, minus the line, which was 2x minus 4 on the bottom. Remember to put the line, since it has multiple terms, in parentheses. This would be with respect to x. I have two regions, and to be frank, it's going to be a bit of a pain because I'm going to have to do use substitution on the square root part. Let's now look at doing this with respect to y instead. If we look at this with respect to y instead, then I'm going to draw my strips from top to bottom or bottom to top in a horizontal direction so that the narrow end is the differential dy. Notice that I always have the same curve on the left and the same curve on the right. This means that I can write it as one integral from the y value at the bottom to the y value at the top. Now I need to find those y values. I already know that the x coordinates of the intersection points are 1 and 4. To find the y value, I can substitute it into either equation, either the square root of 4x on top or the line, or negative square root of 4x on the bottom or the line. I'm going to choose to use the line. If I take my 1 and substitute it, I get 2 minus 4, which is negative 2. And you can see from the graph that that's clearly where it is. If I substitute 4 for x, I get 8 minus 4, which is 4. If I then want to integrate with respect to y instead of with respect to x, I have one integral, and I'm going to write y equals to emphasize it, but that's not technically necessary, from negative 2 to 4. Now I've got to write the equation in terms of y. That means solve for x. Let's go back up here and let's take our equations again and rewrite them in terms of y. We had y squared equal to 4x, which, solving for x, simply gives me y squared divided by 4. The other equation was the line 2x minus 4, which takes a little bit more work. First, I add the 4 to both sides, and then I divide everything by 2. And this gives me x equals 1/2 y plus 2. Now that I have them written in terms of y, I need to remember which one's on the left and which one's on the right. The one to the right has more area between it and the y-axis, so it's greater. And the one on the left has less area between it and the y-axis, so it's smaller. We take the greater on the right and subtract the smaller on the left. In this case, this would give me the line rewritten in terms of y as 1/2 y plus 2 minus the equation on the left, which is y squared divided by 4. Note the differential also changes to dy. Comparing this equation to what we'd have for x, it's far simpler. There's only one integral, and I won't need to use substitution. I can simply do the power rule for integrals. Go ahead and pause the video now to work this one out, and turn the video back on so we can compare our results. Remember that when you integrate with respect to y, the lower limit of integration is the bottom y value, the bottom endpoint of the interval, and the upper limit of integration is the top endpoint of the closed interval, and then it's right function minus left function. In this case, we can simply apply the power rule for integrals, and when we work it out, we get 9 square units. Let's go back and check and make sure we think that's reasonable. Looking back at the original area that we have right here, 1 square unit would be given by this tiny little square there. And the area that we're looking at is the area between the two curves, which does indeed seem to have about 9 squares of that shape inside of it. Let's look at another example where we can use integration with respect to y. In this particular problem, we're given the equation x equal y squared minus 3, which is already solved for x, which makes it easier to go with respect to y. The second one is not solved for x, but it is y equal 1/2 x, a line, and lines are relatively simple to solve for x. When we look at the region that we have here, again, let's imagine what would happen if we wanted to integrate with respect to x or with respect to y. To do that, we know that we're going to need where they intersect. So let's find the points of intersection now. They intersect when they're equal to each other. Because this one is solved for x and this one is solved for y, I can take this expression and substitute it for y in the first. This would give me x equal to 1/2 x quantity squared minus 3. This would give me x equal to 1/4 x squared minus 3. Again, this is a quadratic equation, so I want to move everything to one side and get 0 on the other. It also would be simpler if I didn't have the 1/4, so I can multiply every term by 4. Rewriting, this would give me the equation 4x equal to x squared minus 12, which becomes x squared minus 4x minus 12 equal to 0. This does factor as x minus 6 and x plus 2. This gives me two possible solutions, x equals 6 and x equal -2, which do appear to be the places where the two curves intersect. But if I'm going to go with respect to y, I need the y values as well. If x is 6, half of 6 would give me a y value of 3. And this gives me the ordered pair 6, 3. If x is -2, half of that will give me -1. And this gives me the ordered pair -2, -1. Now that I know where they intersect, let's look at how we would set up the integrals if we went with respect to x or with respect to y. To go with respect to x, we have to draw the strips vertically. Notice that on this side, that puts the upper arm of the parabola above the lower arm of the parabola. Then it changes at -2, -1 and becomes the upper arm of the parabola above the line. This would make it split into two regions. And I would have to write the equation of the parabola, which would give me a square root, which would make it more difficult. If I do left-right, and I instead integrate with respect to y, then I draw the strips horizontally so that the differential is the narrow end dy. In this case, from the bottom of the region to the top, I always have the right opening parabola on the left and the line on the right. You can tell by which end of the horizontal strip touches which graph. Let's now write the integral to integrate with respect to y. I'll be going from the lower y value of -1 to the upper y value of 3. And I forgot to write this one down. Then I need to have for the integrand the right function minus the left. The right function needs to be solved for x in terms of y. Currently, it is not. Let's take this equation, y equal to 1/2 x, and rewrite it as x equal. That just simply requires multiplying by 2. So I get x equal 2y. It's on the right, so I get 2y minus the parabola, which is on the left. That's already solved for x, y squared minus 3. Notice because it has two terms, it must go in parentheses, and I distribute the negative. Now that we have everything simplified, we can go ahead and apply the power rule for integrals to integrate this one. Go ahead and pause the video to work it out now. When we apply the power rule, we get the antiderivative function y squared minus 1/3 y cubed plus 3y, which we need to evaluate between y equal -1 and y equal 3. substituting in the values and simplifying the arithmetic leads us to a final answer down here, if I can scroll far enough, of 32/3 square units, or 10.6 repeating square units. Let's now look at the original graph and make sure this seems reasonable. If we look at the original graph, again, we want to see what 1 square unit looks like, which is 1 square there. Then we look at the region in here between the two curves and see if we can buy that there are just over 10 of them in there. And it does seem reasonable. So because I know I've done the calculus correctly, I can have confidence that I've found the exact area between the two curves. I could have done it with respect to x, but it would have been far more difficult. Let's now look at one more example of integrating with respect to y. In example 9, we want to find the area between the curves of y minus 2 squared, all divided by 3, equal to x, and y equal 8 minus x. Looking at the region here, again, you can see we have a right opening parabola. Right opening parabolas are not ideal for integrating with respect to x. We've seen this before. However, in this case, if we integrate with respect to y, we always have the line on the right and the parabola on the left. Go ahead and pause the video, work this one out on your own, then turn it back on so we can discuss. Let's now discuss example 9. In this case, I went ahead and took the second equation, y equal 8 minus x, and put it in terms of y, solved for x, and got 8 minus y. I needed to find the intersection points, whether I was going to do it with respect to x or y. So I took the two equations, solved for x, and set them equal to each other. In this case, I had a factor of 1/3 on the left. So I multiplied every term in the equation by 3. And then I multiplied out the y minus 2 to get y squared minus 4y plus 4. I subtracted the 24 and added the 3y. Combining my like terms gave me the quadratic equation y squared minus y minus 20 equals 0. This factors into y minus 5 and y plus 4, which gives me two y values, 5 and -4. Then I use the equation of the line to find the corresponding x value in case I thought it was better to integrate with respect to x. Now that I had the intersection points of 3, 5 and 12, -4, I took a look at what it would take to integrate with respect to x or with respect to y. With respect to x, we draw the strip vertically. It sounds counterintuitive, but the narrow end is the differential dx. Notice that I have the upper arm of the parabola over the lower arm of the parabola up to the first intersection point. Then I have the line over the lower arm of the parabola to the second intersection point. This would require two different regions and two different definite integrals. I would also have to solve the equations for y in terms of x. Doing that will give me the square root of 3x plus 2 for the upper arm and the negative square root of 3x plus 2 for the lower arm. Then I would have to integrate with the upper arm minus the lower arm from 0 to 3, and then integrate with the line minus the lower arm from 3 to 12, the x coordinates of where it intersects. I know I'd have to use chain rule on the square root, and I know it probably wouldn't be very pleasant. So I took a look at what I would do if I were to integrate this instead with respect to y, drawing strips from the top to the bottom, allowing the narrow edge to be the differential dy, I notice that I always have the same function on the left, which is that sideways opening parabola, and the same function on the right, which is the line. This tells me I can write it as one region instead of two. I integrate from the lower y value where they intersect, which is -4, to the y value of the upper intersection, which was 5. Then on the right, I have the line, which I solve for x to get 8 minus y, minus the right opening parabola, which was given to me already as the quantity y minus 2 squared, all divided by 3. Now the rest of it is just simply calculation. I'll go ahead and scroll down so you can see what I did. The first thing I did was pull the 1/3 to the side and multiply out the binomial. Then I distributed the 1/3 and I looked at the 8 minus y and the distributed polynomial to see if I had any like terms. I had two constant terms, 8 minus 4/3, which gives me 20/3, which I color coded. Then I had two y terms, minus y and plus 4/3 y, which gave me a combined 1/3 y. There was no like term to combine with the radical or the squared term, minus 1/3 y squared. Once I had a simplified integrand, then I chose to go ahead and apply the power rule for integrals. After applying the power rule for integrals, I substituted the upper limit of integration minus the lower limit of integration, simplifying as I could at each step. When I finally worked this out, it gave me 60 plus 3/2 minus 21. And this became 39 plus 3/2, which becomes 81/2 or 40.5 square units. Now let's take a look back at the picture to make sure that this is a reasonable conclusion. When we look at the original picture, I've highlighted in blue now the size of 1 square unit. I actually counted approximately the squares in the upper part above the x-axis and was at 21 when I stopped. It does seem reasonable to me that the amount of area shaded in yellow is 40.5 square units. We've discussed how to integrate with respect to x and how to integrate with respect to y, and we've practiced a little bit at determining which one might be easier. Let's take a look at some more examples where instead of integrating, we just want to determine which would be simpler. Determining which one would be simpler means looking at the strips. I can't emphasize enough how important drawing those little rectangles is. When we get to volumes of revolution in the next section and the following one, they'll be critical. So draw those rectangles. Remember that when we're integrating with respect to the independent variable, it's the above minus below or upper minus lower. When we're integrating with respect to the dependent variable, it's right minus left. The strips really tell the whole story, combined with how easy it is to solve the equation for either y or x, and whether those expressions are easy to integrate or not. If the equation causes a change in what's above and below, think about maybe integrating with respect to y. But if you're looking with respect to y and what's on the right versus the left changes, perhaps integrating with respect to x would be simpler. Remember that your vertical strips, integrating with respect to x, have the differential dx as the narrow side, and the horizontal strips, integrating with respect to y, have the narrow ends on the y side with the differential dy. Sometimes it's just as hard with both orientations. Let's look now at example 10. In example 10, you can see that I have a graph of what appears to be x squared and the square root of x. Do you think it would be easier to go with respect to x or y? If I'm looking at this and I want to draw my rectangles with respect to x, then I draw them vertically from top to bottom, moving from the left to the right. Notice that the square root is always on top and the parabola is always on bottom. It's simple to solve these equations for y in terms of x. I can also find where they intersect by setting the two equal to each other. In order to solve, I need, of course, to go ahead and square both sides, knowing it might introduce a false solution. This gives me x to the fourth equal to x. Then I go ahead and I move everything to the left. Do not divide by the variable. If you do, you're losing the solution of the origin. When I factor, this becomes the difference of two cubes, which does factor. It gives me x times x minus 1 times x squared plus x plus 1. The quadratic will give me an imaginary solution, so I know it won't be on a real graph. The first two, however, give me the two intersection points that I'm looking for. And then I can use either equation to find the y value. In this case, the y value would be 0, and here the y value is 1. If I want to integrate with respect to x, I would go from x equals 0 to x equal 1, and I would have the square root of x minus x squared with respect to x. How about with respect to y? If I'm going to go with respect to y, I draw the strips horizontally, moving from the bottom to the top as y increases. I'm looking to see if I always have the same function on the right, which I do, it's my parabola, and the same function on the left, which I do, it's my square root. That's not enough to tell me this is simpler. I also have to think about the equations. I have the equation y equal x squared, which would have to be solved for x. Normally, this would give me x equal plus or minus the square root of y. But it turns out that if you write it this way, this right arm that you see here becomes x equal the positive square root of y. And the arm on the left, which you see here, is given by x equal the negative square root of y. Since ours is the right arm, we would use the positive square root of y. Then we would have to solve the square root function for x in terms of y. This would be y equal the square root of x. We'd have to square both sides, which would give us x equals y squared. To do it with respect to y, I would integrate from y equals 0 to y equal 1. And I would have on the right the parabola, the right arm, which would be square root of y, minus the square root function, which is y squared. Notice the differential is dy. These are not so different, are they? In fact, they're the same, but with respect to a different variable. Let's now take a look at another example, example 11. In example 11, we're trying to determine whether we should go with respect to x or y for x equal y squared minus 4 and y equal x divided by 3. Again, to do it with respect to x, I draw the strips vertically from the left side to the right side as x increases. Notice that it does change. I have the upper arm of the right opening parabola over the lower arm of the right opening parabola, and the upper arm over the line. Going with respect to x would probably not be the way to go. Let's look at what it would be like to go with respect to y instead. With respect to y, I draw my strips horizontally, going from the bottom to the top as y increases. In this case, I always have the line on the right and the parabola on the left. So it would be simpler in this case to go with respect to y. If I wanted to integrate with respect to y, I need to find the intersection points. Let's go ahead and write down the equations so we can find them. We have x equals y squared minus 4, the right opening parabola, and y equals 1/3 x, the line. I can substitute the value of y into the other equation, or I can take the line and solve it for x by multiplying by 3, and then setting the two x's equal to each other. This would give me 3y equal y squared minus 4, which becomes y squared minus 3y minus 4 equals 0. It factors to give me y minus 4 times y plus 1. This gives me two y values, 4 and -1. Then I can use my equation for x, the simpler one, 3 times y, to find the x coordinates that correspond to that. In this case, I would get 12 and -3. To integrate then with respect to y, I would integrate from the lower y value of y equal to -1 up to 4. I would have the right function, which is the line, 3y, minus the left function, y squared minus 4. This would be with respect to y. I could set it up to do it instead with respect to x, but it would involve two definite integrals, and because x equals y squared minus 4, a radical as well. Let's go ahead and write down what that one would be. If I were to take the equation x equal y squared minus 4 and solve for y instead, I would have y equals plus or minus the square root of x plus 4. This means I would have to integrate from the left x value, in this case, this makes it even harder. Notice that the far left, in this case, is not given by the intersection point. It's actually at the value of -4. So what I would have to start at -4 for x and go to where they intersect, which we found to be, I'm trying to find it, -3. And in this case, it would be the upper arm, square root of x plus 4, minus the lower arm, negative square root of x plus 4, with respect to x. Then we'd have to integrate from -3 up to 12 with the upper arm, the radical, minus the line, which was 1/3 x. It is far simpler to evaluate this one with respect to y. Let's take a look at two more examples. In example 12, we want to determine if it's better to go with respect to x or with respect to y. The fact that both equations are solved for x is a good indication that probably going with respect to y is better. Let's see why. If I draw the first one with respect to x, then I make my strips vertical. Notice that this means I have line over the lower arm. However, after I get to the second intersection point, it becomes the parabola over the parabola involving two regions. If I instead look at integrating with respect to y, I can draw the strips from the bottom to the top or the top to the bottom with the differential being the narrow end dy. I always have the left opening parabola on the right and the right opening parabola on the left. And that means that it is simpler to go with respect to y. You would need to find the intersection points in order to know what those y values are. Go ahead and pause the video to find them and write the integral with respect to y only. Then turn the video back on so we can check our answers. When you set the two parabolas equal to each other and solve, you should have gotten two intersection points at -3 and 2. Those are the y values of the intersection points. Then when you're looking at the graph, you again notice that it's the left opening parabola on the right. So you write that one first and subtract the right opening parabola from it. Be sure to put it in parentheses and distribute the negative. And then you would integrate. We have one last example to take a look at, which is a little bit of a more complicated region. In this particular one, you can see that we have a parabola opening to the right in blue and what appears to be a cubic in terms of y in purple. We have two regions that are trapped in here, a small region just above the origin and a larger one above it. Again, let's imagine trying to go with respect to x, and then we'll imagine going with respect to y. With respect to x, I have, cubic over cubic, and then cubic over upper arm of parabola. And in this region, I have upper arm over lower arm of parabola, and this region, cubic over cubic. This would be an absolute nightmare to integrate with respect to x. Don't even consider it. It's got to be better with respect to y. When we look at it with respect to y, and we draw our strips horizontally with the differential dy on the narrow end, we can see that it does give us two regions. This is still far better than the 4 regions to go with respect to x. In the upper region, we have the right opening parabola on the right and the cube on the left. In the lower region, it reverses, and we have the cubic on the right and the right opening parabola on the left. Let's pause the video so you can find those intersection values for the y, and then write the integral. When you set the two equal, you do end up with a cubic function, but there's a greatest common factor of y, which can be factored out. That gives you a quadratic factor, which factors further into y minus 4, y minus 1. We have 3 intersection points when y is 0, 1, and 4. This means that we can set it up as 2 separate regions. But again, if we'd gone with respect to x, there would be 4. In this case, we're going to get the cube function minus the parabola from 0 to 1, since the purple is on the right side of the blue. Then in the second region, from 1 to 4, we have the parabola in blue on the right side of the cube, and so we subtract the cube from the parabola. This is the end of the video on section 6.1. In the next section, we take a look at finding the volumes of solids. We start with solids that have a common cross-section shape, though of different sizes. And we also look at taking a graph and revolving it around either the x or y axis to get a solid, and then we find the volume of that solid. See me for the next video.